So good morning, everyone. So I will present our project OmniLedger, which is a secure scale-out decentralized ledger, and we achieve that via sharding. So this is a joint project between quite a few people, and some of them should look familiar to you because they also presented here or gave workshops. So this OmniLedger was designed by Lefteris, Nicholas, Linus, Eva, and Brian, and myself. So my talk is structured like this. I first will present some motivation on why we actually want to do sharding. Then I will introduce OmniLedger, our proposal. Then I will go over our implementation and evaluation of the system, and finally conclude. All right, so to motivate, I have a question to you. So what are we using blockchains for, or what are people using blockchains for? ICOs, yes. What else?
Gambling.
Gambling, yes, very good. So that's actually one of the big things, right? People like to do games on the blockchain. And a while ago, there was this game called CryptoKitties, which was deployed on Ethereum, which completely stole the whole system because it became so popular that Ethereum could not take the load to operate that game, right? So I mean, that's a little bit of a half-joking example, but it shows very well on what happens if blockchains become more popular and become more widespreadly used, right? So we need really high-performant ledgers to support all of these applications and whatever comes next. So for that reason, let's have a look on what are the core problems on the scalability issue for current blockchain systems. So at the core of Bitcoin, there is the Nakamoto consensus protocol, which works roughly like this. You have miners in the network, they are connected to each other, and they mine blocks by solving these cryptographic puzzles. And here the yellow node is the latest miner that found the latest block, and he extended the Bitcoin blockchain. So this mechanism has several drawbacks. First of all, there is a huge transaction confirmation delay, at least in Bitcoin, where the time that it takes to solve these cryptographic puzzles and thereby publish a new block is at least 10 minutes. So that means if you, as a client, are sending a transaction to the Bitcoin blockchain, it takes at least 10 minutes until it appears there and you can see it as confirmed. Then the next problem, on top of these 10 minutes delay, you also have only a 1 megabyte block size, which when you do the math translates to roughly 4 transactions per second that the system can sustain. And to give you an example on what that compares to, 4 transactions per second is roughly the amount of throughput that an IKEA does on a busy Saturday. Another problem is that Bitcoin provides you only weak consistency, which means once the transaction appears on the blockchain, you still have to wait several blocks before you can be really sure that it stays there. Because in the last part of the blockchain, there can still, forks can still appear, right? So once you have up to 6, once the transaction is 6 blocks down in the blockchain, the probability that the fork still happens is reasonably low. And of course the last problem, but we won't talk too much about that here, is that proof of work mining consumes a lot of energy to sustain all of that. So the proof of work mining you need to solve these cryptographic puzzles. All right, so now you want to think, okay, this sounds like a problem also in cloud computing, for example, right? Where people just throw more hardware onto the issue, and then it scales better. But it's not so easy here. So, because if you add more resources to the network in the form of miners, for example, that doesn't change the fact that a block still takes 10 minutes to be published, and the block size is one megabyte, right? So that doesn't change anything on the latency or on the throughput on the long term. And also, it doesn't change anything about the consistency problems that I mentioned before. So what we really want from our next generation scalable ledgers is something like that. So the green line shows you Bitcoin. On the x-axis, you have the number of validators, right? So if you have n validators, Bitcoin gives you 4 transactions per second. If you have 2n validators, Bitcoin gives you 4 transactions per second. If you have 5n validators, the same thing. So it doesn't change anything if you add more resources. But from an ideal system, we want to leverage the additional resources that we have available in the network, right? So the blue line shows you what we actually want to achieve. With more resources, we want to get a linear increase in the throughput, ideally. So, and this is a property which we call scale out. So the throughput increases linearly with the available resources. And when you look through the distributed databases literature, there's a technique called sharding. And sharding allows you to achieve scale-out performance. So how would you take this from this classical distributed databases towards the blockchain world? You can imagine like that you group the validators into distinct subsets, and you assign your validators to do different blockchains. Here, the yellow and the green one. And then the yellow validators would validate the yellow transactions, and the green ones would validate the green ones. And thereby, you now doubled the throughput in the system. However, when you do that, you come up immediately with 2 questions. Namely, first of all, how do we assign these validators to the shards? And the second one is, how do we send transactions across shards, right? We want to be able that persons who have accounts on the green blockchain can pay people on the yellow blockchain and vice versa. Otherwise, the utility of that strawman system would be very low. So with those 2 questions in mind, let's have a look on what people have worked on before. So here you see 3 goals that we want to achieve in our sharded or in the next generation ledgers. So we want to have decentralization, of course. We want to achieve security, and we also want to achieve scale-out performance. In 2016 at CCS, there was a paper called A Secure Sharding Protocol for Open Blockchains, which introduced Elastico. And Elastico is here on the axis between scale-out and decentralization. So it sacrifices, which means it sacrifices security. The problem with Elastico is that you use proof of work to assign validators to shards. But that's not unbiasable because miners can drop blocks and thereby bias basically the randomness. And also when you look into Elastico a little bit closer, you see that the failure probability of the system increases with the number of shards that you have, which you don't want, of course. So that's why it sacrifices security. Another system, which is called RS Coin, was presented at NDSS, which is called Centrally Banked Cryptocurrencies. And it's on the scale-out and security axis. So RS Coin sacrifices decentralization to achieve both scale-out and security. So you have a central coordinator that takes care of the sharding. And in RS Coin, you also do not have a BFT consensus mechanism that secures the blockchain. So there it might happen that a client who colludes with the coordinator can double spend in the system. Then on the decentralization and security axis is the system that Lefteris presented yesterday called Biscoin. And yeah, I won't say that much more here. So Biscoin has good performance, but it doesn't scale out, as Lefteris mentioned yesterday. So, and in this talk, yeah, I will present OmniLedger, which achieves all 3 of those properties. All right. So when we started looking into OmniLedger, we had the following goals, which are in 2 categories. We had 3 security goals here in blue, which is we want to achieve full decentralization, so no trusted third parties or single points of compromise. We want to have shard robustness, meaning that From time to time, you need reconfiguration events in your system. So, but throughout those times, we want to keep the shards operational. We don't want that the shards go down and then you have to rebootstrap those shards, right? And we also want to have secure transactions, meaning, especially across shards, meaning that transactions commit atomically or they abort eventually. And then we also had 3 performance goals, namely scale out, right? So we want to have linear throughput, as I mentioned initially. Then if you have very high transaction throughput systems, your blockchain will of course grow also very rapidly, which leads you to eventually having storage problems, right? Because somebody has to store the entire history, so we also want to get better there. And also we want to have low transaction confirmation latency, right? So when I send a transaction, it should be immediately or like very quickly confirmed, and we don't want to wait for 10 minutes or more until it's sure that the transaction was committed to the system. So to further motivate, I will start with the strawman approach, which we call simple ledger. Simple ledger evolves in epochs, which are denoted here by E. And in simple ledger, you have a shard coordinator, which regularly issues a shard configuration. And then the validators take that configuration, check in which shard they are, start setting up the shards with their peers, and then once that's done, they can start processing transactions. So here in that example, you see on the top is the shard coordinator, then the validators. Once they have the configuration, they get assigned to one of these 3 shards, yellow, green, or blue. And once the setup is done, they start processing transactions. So that, of course, works. It gives you scale-out performance, but it has several problems, right? So first of all, the shard coordinator is a trusted third party. Then it also has this problem when the shards are reconfigured, the shards go down basically, and you need some time to rebootstrap those shards. There is so far also no cross-shard transaction support, so basically what we just generated are 3 different blockchains. Then we also have a few performance drawbacks, namely the Bitcoin failure mode, which means that the original Bitcoin system was using tree structures to get very high performance. But you have problems here when nodes which are high up in the tree go down, then you cannot communicate with the whole subtree, or you need to reconfigure that subtree, or even worse, if the leader goes down, then you need to make a few changes, which is also costly. Then, as I already mentioned, you have high storage and bootstrapping costs because Bitcoin is a very high throughput system, so the blockchains there will grow very fast. And you also have a throughput versus latency trade-off, meaning that when you want to achieve good throughput, you need big blocks. But to communicate and process these blocks, this will take time, right? So communicating just a 1 megabyte block is much quicker than communicating a 32 megabytes block. But 32 megabyte blocks gives you much better throughput than 1 megabyte blocks. So, and we also want to get rid of that trade-off somehow. All right, so here's a roadmap how we go from simple ledger to OmniLedger in 6 steps. First of all, we will introduce randomized sharding. Then we will tackle the problem of secure system configurations to have no downtime during this reconfiguration events. Then I will introduce an atomic cross-shard transaction protocol. Then you enhance the failure resistance of Bitcoin by having more robust communication patterns. Then we do something which is called blockchain pruning to reduce the size of the amount of storage that you need. And then we introduce a mechanism called trust but verify to tackle that trade-off between high throughput and low latency transaction validation. So I will here only talk about these 3 points. They are the most important ones, and also because of time. All right. So if you remember, in the very beginning I said, okay, how do we, there is this open question, how do we assign validators to shards, right? So, and we have basically two options. The first one is we do so deterministically, right? We say maybe the first 5 nodes go to the first shard, the next 5 nodes go to the second, and so on and so forth. However, that's a problem because the adversary can totally predict that, right? And he can potentially position his nodes in such a way that he can corrupt an entire shard. And as Mustafa said in his talk, that's a very bad situation because then these nodes can corrupt the entire system through bad cross-shard transactions. So, but what's a lot better is we do so randomly, because then when we use unbiasable public randomness, the adversary cannot control or predict that assignment. So then the next question becomes, how do you ensure also the long-term shard security against an adaptive adversary, right? Once you've assigned your nodes, the adversary might have some time to corrupt nodes adaptively afterwards. So, and there the two solutions are basically you make the shards large enough, and you also periodically reassign the validators to shards, which are these reconfiguration events that I mentioned before. And when you do the math, then you see, which is depicted here in the graph on the right-hand side, on the x-axis you see the adversarial power, and on the y-axis you see the approximate shard size that you need. And for example, if you want to be resistant against a 25% adversary, you roughly need a shard size of 600 to be secure. So yeah, as I said, the challenge here is how do you do unbiasable, unpredictable, and scalable shard validator assignment? And our solution is we use public randomness. And here we combine a VRF-based lottery with an unbiasable randomness protocol. Namely Randhout, that Eva presented in the previous talk. And if you remember, Randhout needs a leader or a client basically to execute the protocol. He's there for coordination. So, but again, we cannot pick the leader deterministically because then the protocol might fail a bunch of times. So that's why we use a VRF-based lottery to pick from all the validators that are out there one person who becomes the leader. So then this leader executes Randhout. Why are we doing this? Okay, now the leader might have been picked randomly, but this might still be a bad guy, right? So we cannot trust him fully to do the shard validator assignment. So we want to take the input of all the validators that are available in the system, and that's where Randhout comes in, which does exactly that. See the last talk. And once we have the verifiable randomness, we can use it to assign the validators to the shards. Here again, we have a yellow, blue, and a green shard. All right. So then the next challenge was that we wanted to have a protocol for atomic cross-shard transactions. And to do that, we again look back into the literature on distributed databases, and there are systems which are called, or protocols which are called two-phase commits, where you have a coordinator and a bunch of servers. And the coordinator, so yeah, as it says, there are two phases in the protocol. First, you have a voting phase where the coordinator sends a query to all the servers, asking them, can you execute that transactions? And all of the servers reply yes or no. And then the coordinator collects the replies and checks if everybody voted yes, then he can tell them, okay, now please commit. And if there's one of them who says no, then you execute a rollback protocol. So that looks already promising. However, if you are in a Byzantine setting, then you have the problem that the servers can be malicious. So one of the servers can always vote no, and basically you don't have any liveness anymore in the system, right? So, but taking that idea further, what you then realize is once you have this shard assignment, random shard assignment, and you have a Byzantine fault-tolerant consensus mechanism within the shards, you can consider basically all the shards honest, right? So now you take it basically one abstraction level higher and consider your shards as the honest processes in the system. So to give an example here, which is basically this the atomics protocol, which does these secure cross-shard transactions. You have an initialization phase where a client says, I want to execute this transaction. Here in the example, it has inputs in shards 1 and 2, and it pays somebody in shard 3, the yellow one. And then the client sends this to the 2 input shards. The 2 input shards lock the funds and send acknowledgements back to the client. The client collects all of these acknowledgements. And then if all the input shards could lock the funds, he can go to the output shard and say, here I have a proof that you can commit the transaction in the yellow shard. On the other hand, if one of the shards aborts this process, here in the example, the green one, he sends back an error. Maybe the client does not have enough funds in his account in the green shard. Then basically the client executes a rollback mechanism where he goes then to his input shard that already has locked the funds and says, please unlock my funds. And thereby he can reclaim the transaction inputs. And the last point that I want to mention is how you can deal with the throughput versus latency trade-off. How are we on time?
We've got another, I would say 10 minutes.
Okay, good. Where we introduce this trust but verify transaction validation mechanism. So as I mentioned initially, if you have big blocks, you get high throughput, but bad latency confirmation, right? Because it takes some time to propagate the blocks and to process them. On the other hand, if you have small blocks, you have low throughput, but a high transaction confirmation latency because small blocks propagate fast and they can be processed very fast. So now we ask ourselves, okay, how can we manage to combine these two approaches, right? So and what we did is basically we introduced this mechanism where within a shard you have one big group of validators who are there for the verification of large blocks and for adding them to the blockchain. And you have a set of smaller subshards, here the green ones, which are the optimistic validators, and a client sends his transaction always to the optimistic validators. They check it against their current state and give them very quickly a feedback just on that transaction. And then they forward those transactions to the bigger subshard, which re-executes the transactions and sees and checks if it's valid according to the blockchain of the shard. And thereby you can see, okay, the client gets very quick feedback on his transactions, and the core shard can aggregate, batch those transactions together into very big blocks, and thereby he gets good throughput. And this is perfectly fine, because if you consider like you buy just a coffee with your cryptocurrency, then it's okay that you get a very quick confirmation, right? Because the chances that somebody is attacking you for, I don't know, €3 or so is very low. On the other hand, when you have a big spending, you might want to wait until the core validators have really revalidated everything and put the transactions into the blockchain. So coming to the evaluation, this slide might look familiar because that's like exactly the same one that Eva showed before. So we basically implemented all of that in Go using our authority framework, the Bitcoin consensus mechanism. We also implemented the atomics cross-shard transaction protocol. This is all based on the Kyber crypto library, the ONET network library, and the authority framework. And the DTOLab setup uses 48 physical machines, and they were very well equipped machines. So, and to get realistic network configurations, we artificially reduced the bandwidth and also put a 200 millisecond round trip time latency, which roughly models the round trip latency that you have on the internet. So the first thing we wanted to evaluate is, okay, does OmniLedger really achieve scale-out performance? And here you see a graph. On the x-axis, you see the number of validators and shards. And on the y-axis, you see the number of transactions per second that OmniLedger can execute. And as a baseline, you also see Bitcoin here on the low end. It does like constantly just 4 transactions per second. Versus when you look at OmniLedger, with 70 validators and 1 shard, you get roughly 440 transactions per second. If you double that amount to 140 validators and 2 shards, then you get 870 transactions per second, and so on and so forth. And when you look at the line, it's really gives you a linear throughput increase in the number of validators that you have. Then, on the other hand, we also wanted to look into the question, what is the maximum throughput that OmniLedger can give you? Here, again, on the x-axis, you see the shard size and the adversarial power. And on the y-axis, you see the number of transactions per second that OmniLedger can do. So if you have a very, very weak adversary, which, for example, only corrupts 1% of the nodes, then you can live with shards who are just like of the size of 4 nodes, and thereby you get like really, really high throughput. If you go to a more permissionless setting, on the other hand, for example, if you have a 25% adversary, you need a number of validators in a shard of around 600. And there you can see, you get roughly 2,000 transactions per second. And something in between, when you have a 12.5% adversary, you actually get more throughput than Visa is doing on average. And then the final question that we had, how does OmniLedger do with this latency throughput trade-off? So here you see, in the first row, you see just OmniLedger in a regular setting without this trust but verify mechanism, where you get, on the very right-hand side, with 600 validators and a 25% adversary and 1 megabyte blocks, you get a confirmation from the client within roughly 15 seconds. When you split that up and you do this trust but verify validation, you can check the next 2 rows. And here it improves already quite a bit. So to get a first confirmation, a client only has to wait 4.5 seconds. And then to wait for the consistency to the re-evaluation of the core validators, he needs to roughly wait 1 minute. But then you have also 16 megabyte blocks in your blockchain, which gives you very high throughput. And when you compare this to Bitcoin, this is quite similar. You have like first a confirmation. This is like as soon as the transaction is included in the blockchain, which takes roughly 600 seconds, which are these 10 minutes. And for consistency, you have to wait 6 blocks, which translates to 1 hour or 3,600 seconds for 1 megabyte blocks. All right, so thereby I want to conclude my talk. So I presented OmniLedger, which is a secure scale-out distributed ledger framework. We use sharding for unbiasable, verifiable randomness generation to assign validators to shards and thereby achieve linear scale-out throughput. We use this atomics protocol to have secure cross-shard transactions. And we use a trust but verify mechanism for breaking this trade-off between low latency confirmation and high throughput. And OmniLedger, I didn't mention that so far, but it works for proof of work, proof of stake, or in a permission setting, whatever you prefer. The paper appeared at IEEE Security and Privacy earlier this year. Here is a link, and the code is available on GitHub. So now I'm happy to take your questions. Thanks.
Thank you, Philipp. I thought that was really clear. We have a question right here.
Thank you. Good talk. I wanted to ask, does the number of shards need to be preset when the system starts? How do you move from 1 to 2 to more?
No. So you can do this adaptively because the system evolves in epochs, right? So and what you assume is you have an identity blockchain running where the nodes sign up their identities saying, hey, I want to be a validator. And if in one epoch there are a lot of nodes joining, then you can, in the next epoch, when you do the reconfiguration, just assign them to new shards or even spin up an entire new shard as you go.
Sergi.
Great talk, Philipp.
Just out of curiosity, do you need to choose if you're doing the trust but verify thing in the configuration, or can any node do it?
So that's yeah, good question. So that's either way. So you could imagine that this is a system parameter, right? When you set up the system, you just say, we always do trust but verify. Right. From a client perspective, it doesn't change much, right? Because if the system has trust but verify, and you don't want to just have the first confirmation, then you just wait for the second step, and then you just ignore it, basically, right? So,
all right.
Yeah.
Cool. Thank you.
Thanks.
Hey, do you have some information on the throughput for cross-shard transactions?
No, we did not do that experiment. That's a good remark. So, of course, if all of your transactions are cross-shard, then your throughput will go down, right? So, but for that you would need, some kind of realistic data points, or you would need to come up with some simulation to do that, and we didn't do that experiment.
And another quick one, where do the 25% come from? Is it a bound, or why did you pick 25%?
So this 25% comes from the fact that the failure probability. Okay, I didn't mention that. So the failure probability from that with 600 validators is relatively good. So we had we fixed a target failure probability in our system that we wanted to achieve. And when you then do the math for the different adversarial powers, then you just, okay, I have 1%, 12.5%, 25%, and so on, and you just check what is the shard size. It was just from the mathematical analysis, so there was not much behind that. Yeah.
So thank you, Philipp.
Okay.
Then